Hey everybody, it's Mr. Carr again. Today we're going to be looking at 10.1 to start our new unit. We're looking at, in this case, sequences in series and then sigma notation. But today we're just going to focus on just different types of sequences. Okay, so what does it mean by that? So what is a sequence? It's an ordered list of numbers known as terms. So the domain of a sequence is a set of natural numbers. So remember, with natural numbers, that is everything above zero and no fractions. So when we look at this, like this is my first term, a sub 1. And that's kind of the equivalent of like with a function f of 1. So my domain here is 1, my range would be f of 1, or whatever that value comes out as. A sub 2 is the second term, a sub 3 is the third, and so on. Okay. So that is just any kind of sequence of numbers that and especially if they a sequence of numbers that has a certain pattern for it. Usually a pattern that involves with that. So what is a recursive sequence? That's a sequence that defines one or more of the first few terms and then defines the terms that follow using the previous terms. So what you're going to see with recursive is it looks like this. If I refer to just any term in the sequence, I'm going to call it a sub n. So like a sub 1 is the first term, a sub 2 is the second, and so on. But a sub n is any term. Okay? If I want to refer to a previous term, like the term that follows right before a sub n, that is a sub n minus 1. That is the previous term to a sub n. If I want to keep going back, if I want to do two terms before that, then that'd be a sub n minus 2, or a sub whatever it is, however many spots I want to go to. Now remember, these are referring to positions in comparison to n. So whatever this a sub n is, the one that's right before it is a sub n minus 1. If I want to go above it, I go a sub n plus 1. I could say that as well. But usually with a recursive, we refer to the previous terms. Okay, so we have a handful of examples that are pretty straightforward here. So we're just going to analyze and find a pattern. So we want to find the next four terms of the sequence. One way to always check is maybe start with like addition, subtraction. That's a good way to start it. So for example, we got 3 to negative 1. That's the same as minus 4. Negative 1 to negative 5 is also minus 4. And then negative 5 to negative 9 is also minus 4. So I have confidence that my pattern is just going to subtract 4 at each step. So if I want the next four terms, I can do negative 9 minus 4 is negative 13. Negative 13 minus 4 is a negative 17. And then I get subtract 4 again and one more time. There's my four terms. So negative 13, negative 17, negative 21, and negative 25. Okay. So let's try this one next. The next four terms of this sequence. So 18, 15, 10, and 3. So again, the goal I want to look at is addition or subtraction. So if I do subtraction, it's going to be minus 3, but then minus 5, and then minus 7. So it's not exactly right there, but I can kind of look at it the second level. This is constant. It's subtracting 2 every time from that. So in this case, if I take the next number, I should be able to predict it's going to be minus 9. And then another number is going to be minus 11, and then minus 13. Okay. And that's, I got to go one more, minus 15. So if I recognize that that second level is the same, then I should be able to fill this out then. So we have 3 minus 9 is a negative 6. Negative 6 minus 11 is a negative 17. Negative 17 minus 30 is a negative 30. And then negative 30 minus 15 is a negative 45. So again, I'm doing 3 minus 9 gives me negative 6. Okay. Oh, sorry about that. So what we're saying there was that, okay, so once I have negative 6, I take that negative 6 was right here. Negative 6 is then subtracted by 11. That's how I get to negative 17 and so on. Okay. So find the first four terms of this sequence given that a sub n is equal to n cubed plus 1. So that's my rule right here. I want to find the first four terms. So I'm looking for a sub 1, a sub 2, a sub 3, and a sub 4. Okay. So in this case, it's just going to work like any other function. I'm just going to plug in my values in. So this is going to be 1 to the third plus 1, which will give me 1 to the third is 1 plus 1 is 2. Here I'm going to have 2 to the third plus 1. It's going to be 8 plus 1, which is going to give me 9. Here I have 3 to the third plus 1, that is 27, plus 1 is 28. And then 4 to the third power plus 1. So 4 to the third is going to be 64, plus 1 is 65. Okay, so that's another way I can do this. Here we have our pattern being defined recursively. So this is that recursive relationship I brought up earlier. So if I give you the first term, a sub 1 is 3, then the recursive relationship is going to follow this rule. So I read through this, I'm going to kind of describe what's going on. Any term in the sequence is going to be 3 times the previous term minus the term number and then plus 2. Okay, so in this scenario, we're also defining n has to be greater than or equal to 2. So we're not going to look at it as a sub 1. There's no like term before that. So in this scenario, we can figure out find the fourth term. To find the fourth term, unfortunately, we got to have like all the terms in a row. So if I have a sub 2, I need to figure out I have a sub 1. So I got to figure out what a sub 2 is, then figure out what a sub 3 is, and then figure out a sub 4. Because everything is in this case, in reference to the previous term. So if I do that, a sub 2 is going to be equal to 3 times the previous term. So 3 times a sub 1, which in this case is 3, minus the term number, so minus 2, and then plus 2. So I just go through this right now. It's going to be 9 minus 2 plus 2. So a sub 2 is just 9. Well, now that I have a sub 2 is 9, that's going to help me find a sub 3, because that's going to be 3 times the previous term, which in this case was 9, minus n, the term number. In this case, it's minus 3, and then plus 2. So 3 times 9 is going to give me 27, minus 3 plus 2. So 27 minus 3 is 24, plus 2 is 26. All right. And now I can use my third term to help me find the fourth term. So that's, again, 3 times the previous term. So 3 times 26 minus the term number. So it's minus 4 and then a plus 2. So we got 3 times 26. It's going to give me 78 minus 4 plus 2. And I do that, I get 74 plus 2 is 76 now. So my fourth term, which like this, I had to go through this process, is 76. I can't just jump right to the fourth term. All right. Now, another thing that happens with these series or sequences, I should say, we can describe them as either being convergent or divergent sequences. So it's a matter of looking at the end behavior of the sequence. Okay. So a sequence that is convergent means that it's approaching a unique number. So sometimes it helps to actually graph it so we can kind of see what that behavior is going towards. Think of it kind of like an exponential function that has a horizontal asymptote. It's approaching a certain number, and as it gets no matter how far we go, keep going higher, higher, higher in our term numbers, it's still getting closer and closer to that value. They can also be divergent, and that's when it does not approach a unique number. Usually it's just going away from it. It's just going to go off to infinity, or there's patterns where it's going to go up and down, but it's going to keep spreading away from each other. So that's what we're going to look at here. And we're going to use our graph here. Okay. So when you're given a rule, you can always just plug this into your graphing calculator and see what happens. This is a little bit tricky because it doesn't create, well, this actually will look really odd in a TI-84. So we're actually just going to kind of look at the plot if we plug some values in. So for example, if we plug 1 in for n, that'll come out to here. Okay, we plug 2 in, drops down here. 3 puts me here, 4 puts me here, and so on and so on. Okay. So in that scenario, we look at this setup because these points are getting closer and closer to the 0 line. This is going to be convergent. Okay. As we go on, the points are just going to keep getting closer and closer to 0. Okay. When I do this one, again, you can kind of look at this one if you plugged in some values. So you plug in 1 here. That's -2 divided by -2 to the first divided by 2 is going to be a -1. So that's that point. So again, you look at that one as we go up, my next sequence is going to go be a little bit positive. Then my next one here for 3, it's going to be negative, but then it's going further away from the x-axis. 4 goes a little further, 5 goes a little further, 6 goes a little further, and then 7 would probably be way off the graph somewhere down here. So that makes this divergent because we are not approaching a unique number here. Okay. And then one more here we can look at like this. So determine if this sequence is convergent or divergent. So once again, if you were to plug in if you're doing this in your calculator, I would suggest plugging in values for n to see what's happening with the numbers, just to kind of get a feel for what the pattern is. Plotting them on a graph is helpful because we can see that that's at first term. My second term is getting close to zero. My third term, my fourth term, my fifth term, and sixth term. You can see that it's getting closer and closer to zero. So once again, that makes it convergent based on that behavior that's approaching zero. Okay, one more example we want to cover today, and we're going to look at what's called the Fibonacci sequence. So this is, suppose that a stem has to grow for 2 months before it is strong enough to support branches. At the end of the second month, it sprouts a new branch and continues to sprout one new branch each month. The new branches grow similarly. How many branches will a plant have after 18 months if no branches are removed? Okay, so it helps to kind of get a feel for the model of what's happening. So for example, here's my tree growing. This is happening after first month, here's my second month, something like that. At my second month, it is now creating a new branch. So we get 2 branches that goes off. Okay, so then every month after this, so my next one, my month 3, this will also grow a new branch here and a new branch here. Okay. So yeah, so it's just, sorry, no, like that model's a little bit off of that one. Sorry, we're only getting 1 new branch on each thing. Sorry, I'm just gonna ignore that. We're just gonna go right to the table that helped to represent this, because honestly, like trying to go through that type of modeling with that one, it seems a little bit awkward. What we're getting is something like this. This is the pattern in a table format. After the first month, there was only 1 branch. After 2 months, there was still only 1 branch. Okay. Then after month 3, one of the branches broke off and came its own new thing. So that's now a second branch there. After the 4th month, we get 1 more branch that pops up, and then so on. So when you look at this sequence of numbers, we can define it recursively, because with a Fibonacci sequence, it is the sum of the previous 2 terms. So if I start here, 2 is equal to 1 plus 1. 3 is equal to 1 plus 2. 5 is equal to 2 plus 3, and then so on. So no matter where I go in this table, it is going to be the sum of the 2 numbers that came right before it. So that's what it looks like this. If a sub 2 is 1, and then as long as we're looking at the 3rd term and more, it's always going to be the sum of the previous 2 terms. Also, a sub 2 and a sub 1 are both 1. It's always going to be that way. There's no easy way to do this type of problem. We are just going to keep going and keep adding this table out until we get to the 16, 17, and then finally 18 months. So for example, 14 months, this would be 233 plus 144. That's what goes there. Okay, and then do the same thing for 15 months with the previous 2. So that's what it looks like here. So after 14 months, we have 377. We add the 377 plus the previous month there is 233. That gives me a 610, and then so on. So we look at 18 months, there should be 2,584 branches, because that is the sum of those 2, 987 plus 1,597. That's how I get to that one there. So again, if no branches are removed, that's what this plant will have, is 2,584 branches after 18 months. So just a quick look at that Fibonacci sequence, but that is it for today. So again, the goal was just to look at, can we identify sequences and then figure out what the patterns are based on the numbers there, but also identify if based on a graph, is it convergent or divergent type of sequence. All right, that's it for today. Take care, everyone.